Hello everyone, welcome. This is a review on organic chemistry test 1. This is one of the tests I gave in person exam, test 1 in OChem 1. It includes chapter 1 to 6. It's a very helpful fundamental basic organic chemistry course, and this is test 1 including 6 chapters. In this video, I have tried to solve all of the questions. There are 16 questions. All of them are solved in the test. So I really encourage you to study them and also review them. And if there are some difficulties, you can go back and see the associated videos in the course. So this exam contains subjects in structure and bonding, acids and bases, functional groups, alkanes, stereochemistry, and thermodynamics. In each one of them, for example, in structure and bonding, you have questions or you have to have understanding in hybridization and resonance. In acids and bases, factors that are affecting acidity, acid-base equilibrium, reactions, and identifying conjugate acids and conjugate bases. In functional groups, you are required to understand intermolecular forces, solubility, and so on. In alkanes, there are questions which ask on Newman projections, cyclohexane conformations. In stereochemistry, obviously R and S assignment. Enantiomers, Diastereomers, and Meso compounds. In thermodynamics, how to calculate delta H of a reaction, and also to draw energy diagrams and are included. So I have tried to solve as an answer key for it. So the exam questions, and also towards the end or in the middle of the video, you'll find where I have solved each one of the questions. And good luck and study well. Okay, let's start solving the problems that were given in the exam 1, and this will help you as a review for future test 2, test 3, and final exam in organic chemistry. This exam covers structure and bonding, organic acids and bases, functional groups, alkanes, stereochemistry, and thermodynamics. So it includes all chapters 1 to 6. All of the lectures are available on my videos at STEM Doctor. You may be able to review them. So let's go back now to each question and try to solve the problems. To name this compound right here, so this is an 8-carbon alkane. Always when you are naming an alkane, you should start from a group that gives you the lowest numbering, which is 2 here, as you see. 2 is carbon number 2 is right here, and here is carbon 6. So this is named as an octane basis. This is octane because it's 8 carbons length, 8 carbons, 1, 2, 3, 4, 5, 6, 7, 8. At 2 you have a bromo. At 6th position we have a chloro and a metal group. This is a metal group right here. This is a chloro. And you should remember that you're gonna name all your IUPAC naming based on alphabetical order. So this would be 2 bromo, 6 chloro, 6 metal, octane. So that's how you would name this. So the second question is, draw the structure for the compound name given. Here you are given a stereochemistry, 1R and 2S. So that means you should be able to draw a 1 bromo 2 chlorocyclohexane. As you know, cyclohexane is this structure, as is given here as the answer key. you have a bromine and a chlorine, as is indicated here. But the point is here, the stereochemistry, how they are configured in space, is important. That means a bromo is an R and a chloro is a 2S. So this is one bromo, that's 2 chloro position. So here I have identified the configuration where bromine and chlorine are actually on this, on a wedge, Br. So this would give you an R stereochemistry, and here is an S configuration for chlorine. So this is one position, this is 2 position. So the ways you are naming, I would just give you as an example. This is a wedge, so priority number 1 is bromine, heavy atom. Priority number 2 is this group right here. And priority number 3 is this group. So priority 3, priority 2. So since hydrogen here is at the back already, hydrogen is in the back, so we can move from 1 position to 2 rotation. So this rotation is clockwise rotation, therefore it is an R. Here for chlorine, for this carbon right here, first of all, the stereogenic centers are this and that. So if you just look at the chlorine, where hydrogen is at the back, chlorine is priority number 1, let's say. Priority number 2 is this group again. Priority 3 is this. So you cannot go from 1 to 2 the way it is. 1 to 2 like this, because the lowest group is, the lowest group is at the back. So we can just go from 1 to 2 directly like that. So it is counterclockwise, hence it is an S configuration. So 1R, 2S, 1 bromo, 2 chlorocyclohexane is drawn as given here. So this is the right structure. So I'll pass now to the second question. So the second question we have right here is, this is the second question in the exam. So in the second question, it asks you, draw at least 2 constitutional isomers for a molecular formula C2H6O. C2H6O. So constitutional isomers are isomers where you have, this is C2H6O, sorry, my pen doesn't write very well. So C2H6O can have different constitutional isomers. So here the most important thing is to know what constitutional isomer is. A constitutional isomer is an isomer of two or three compounds where they have the same molecular formula, but they are constituted differently. For example, here in the exam, this is one of the answers. CH3CH2OH is C2H6O. This is an alcohol functional group, C2H6O. This is alcohol. So in functional group, this is an alcohol. And here you can have also a carbon-oxygen bonding. Here you have only one carbon-oxygen. Here you have one carbon, one oxygen, one oxygen, one carbon. So this is an ether functional group. So ethers are like R, O, R, when R's are representing carbons. That means C, O, C. This kind of bonding constitution is an ether functional group, but for alcohol it is R, oxygen, and the terminal is H, like this one. So an alcohol and ether can be written as two constitutional isomers. They are not related in any ways. They are different species. This is an alcohol and this is an ether. Okay? So we'll proceed to the next question now. Okay, number 3 is asking you to draw a clear Newman projection. This is a question for 4s34 diethylheptane. So this is a compound, 7 carbon, and carbon number 1 is this, carbon number 2, 3, 4, 5, 6, 7. So at 3 and 4 we have 2 ethyl groups as a substituent. So that's what we are trying to show in this question. And the stereochemistry is given for 4s position, but for C3 you don't have the, for C3 it is also not given, but it may not be very important. Yeah, C3 does not have to have any stereochemistry because you have an ethyl group here and an ethyl group here. So that is not a stereogenic center. C3 is not stereogenic center. So, but C4 is. Okay, C4 is a stereogenic center. That's why we have at 4, it's an S configuration. And now the main question is to come up with a Newman projection. So the Newman projection, if you just consider C2 right there, has hydrogen, 2 hydrogens, which are this hydrogen and that hydrogen are these two hydrogens, and C1 is this. So it's looking at from this side, you can see this C2 right there, this C2 carbon, okay, and you have the front one, 2 hydrogens. So at the back you're gonna see this ethyl group, which is this ethyl group right here, on C3, that means at the back you don't see that. So groups at the back on C3 are this ethyl group, which is this one right there, this hydrogen, which is right there, this hydrogen right there, and this whole group, this whole on C4, this is C4 right there, C4. So this is a Newman projection. Now, if you try to identify the interactions, here I have one metal-ethyl gauge interaction, which makes it higher energy. So you continuously rotate to see what other energies, the most stable one, you want to see. So for example, all of eclipse interactions are high energy, so we are not trying to get to eclipse. Eclipse means that if you rotate one of these hydrogens or one of the front groups by 60 degrees, you end up on eclipsed. So rotation by 60 degrees in this case would give you eclipsed form. Eclipsed. And eclipse interactions are very high energy. So that's why I'm just showing here 120 degrees to come up to this. This is still staggered, but there is this C1, which is metal group. So this is CH3 group interacting with this very large group here. So this is another gauge interaction. So this is an example. So if I rotate it by 60 degrees, it's eclipse interaction. So basically the first question was not to evaluate the energy level, but I'm just giving you between these two gauge interactions. This one is a little bit more favored because this is a metal-ethyl gauge interaction, which is less group in terms of size. But here you have a metal group with this very large, how many carbons? 1, 2, 3, 4, 5, 6 carbon system. So that is very high interaction. So it makes it high gauge, high energy gauge. High energy gauge interaction. So basically, this is sufficient to answer the question. Just to draw a clear Newman projection of this would be either this or any one of this would be sufficient. Okay, now we will proceed to the next question. Exam, it asks you to give the possible products of the acid-base reaction. So this is acid-base reaction, to show the arrows which side of the equilibrium, okay, which side of the equilibrium is more favored. That means, is it going to the right or is it going to the left? So that's the question. This needs a knowledge of pKa. pKa means the strength of an acid. High pKa number is weak acid. Low pKa number is strong acid. Remember also this, as a general rule, always a reaction proceeds from a strong acid equilibrium, from a strong acid, always it should go to a weak acid, not the other way around, weak acid. So let's see what happened here. You have cyclopentadiene, it's called cyclopentadiene, and the pKa is 16. The pKa value refers to this proton, and chloride minus, which is a base, in this case, this is a base, and the base snatches off that proton and you generate this cyclopentadiene anion. This is a conjugate base. In another exams, I also wanted students to know which one is the conjugate base or the conjugate acid. In this case, I already gave you which ones are the conjugate acid and conjugate base, but you need to be able to identify. So here pKa of the hydrochloric acid, which is formed by Cl minus and the hydrogen here, is pKa minus 7. So this is a strong acid. Here you have a weak acid. So it is going from a weak acid to a strong acid. So this is not the right equilibrium. The equilibrium should be, in this case, it should shift like this. So the reaction doesn't happen in the forward direction. The equilibrium should shift backwards, because I gave you here the rule. This is the general rule here. From strong acid side, you should go to the weak acid. Here, so this needs a knowledge of the pKa values. So remember some of the pKa values by just memorize some of them. pKa of 10 for this proton right there, this is a phenol. This compound is known as a phenol. It's an aromatic alcohol, pKa value of 10. And you have this strong base. This is an alkane when one proton has been gone. So this is a very strong base. So this is a base. Now you are generating this phenoxide anion, which is a base. And here you have a pKa of 50, a very weak acid, a propane. So you generated propane, which is an alkane. Alkanes have a very low pKa, a very high pKa value. That means they are very weak acid. They cannot be considered as an acid, but there is a measure of pKa value of 50. So you are generating propane. So this reaction, as shown, satisfies the rule. Strong acid going to weak acid, because pKa value of 10 is a relatively high, a stronger acid than pKa of 50. The third one, here I have a propane anion, which is the same here, which is a base here in this case, base. And you have a pKa value of 44 for one of these protons. Any one of them are equivalent. This is an alkene, a pKa of 44. So if I were asked, this is a pKa of 50 because it's a propane again. So which direction the reaction would proceed? It is in the indicated direction. It should go this way because from 44 I'm going to 50, that is a weak acid. This is a relatively stronger acid, and I'm going to a weaker acid. So the equilibrium is favored into the right direction. So it's in the right direction. So here the equilibrium should shift to the left, here to the right, and here to the right as indicated. Here the equilibrium, okay, this is ammonia. Remember, this is ammonia, NH3. And here you have this pKa value of 4.5 for that proton. That means this is benzoic acid. This is called benzoic acid. Benzoic acid has a pKa of 4.5, and ammonia is a strong base. Taking away that proton, you have a benzoate anion, which is the conjugate base, and you have ammonium ion, which the proton has been transferred to this. So the base has taken away the proton. Now it is NH4 plus. It is a conjugate acid, and the pKa value is 9.3. So if you compare 4.5 to 9.3, the reaction should proceed to the right side. So this is how you would answer this question number 4. So we'll continue to the next question. Okay, question number 5 is not very difficult. It's a very easy question. In a molecule with C2H4 molecular formula, how many sigma and pi bonds exist? Draw the stick structure showing sigma and pi bonds. If you just look at C2H4, and if you were to calculate how many rings, how many double bonds they would exist, that means the degree of unsaturation, we call it, it's only 1. That means it can only have one unsaturation. Okay? What it means is one double bond or one ring system. But for C2H4, we can have one double bond. To have a double bond, as in this structure, as you see in the answer, you can have this carbon-carbon double bond, and the hybridization here is sp2. This carbon is sp2 hybridized, and if you count the number of sigmas, this is a sigma bond, this is sp2, this is 1s with sp2 hybridized orbital interaction, 1 sigma bond, another 1s with sp2 interaction, that is second sigma, third sigma, fourth sigma, and there is one sp2 sp2. This, the lower sigma, this sigma bond is the interaction between hybridized sp2 sp2 interaction. Always hybrid orbitals form sigma bonds. So I have 1, 2, 3, 4, 5 sigma bonds, and from unhybridized py interaction, you have a pi bond, 1 pi bond. So this is the interaction. Please refer to my lectures on sp2 hybridization. You'll find it in a video, and it explains all of how hybridization works for sp2, sp3, and sp as well. So this is a py-py interaction, which is this. So basically, the orbital diagram of this looks like this is equivalent to what I have already there, 5 sigmas and 1 pi. And if you were to draw just the orbitals look like this. This is sp2, sp2. This is carbon. This is this. This is sp2. This is sp2. This is sp2. This is sp2 hybrid orbitals. And these are the hydrogens. These are the hydrogens right there. This is the hydrogens. These are the hydrogens. Okay? And the unhybridized py-py interaction, if I draw them with a different color, these are like this, standing up, and that is the pi bond. So this is the pi bond. The rest are, this is sigma, this is sigma, 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 sigma bond, and this one is another sigma, but this one is pi. So the answer basically is this, 1 pi and 5 sigma bond. So we'll continue to the next question. Okay, now let's go to the next question, number 6. Identify the functional groups indicated in the compound. This is a complex compound, but it's only sufficient to know the functional groups, how this compound, what it is containing. So if we just look at number 1, it's an ether, as you see in the question, in the answer, it's an ether compound. So the reason is you have a carbon, oxygen, another carbon. So it's basically number 1 is ROR. So this kind of linkage is an ether functional group. So this is number 1. Number 2, you have a carboxylic acid. Carboxylic acid is a carbon-oxygen double bond in OH. So basically, the functional group is RCOOH. So this is what you see. This is a carboxylic acid. So this number 2 is carboxylic acid. So I want to mention also some of the hybridizations. Here for example, this carbon, the CO carbon double bond is always sp2 hybridized carbon. This oxygen right here is as a single bond. It is sp3, and the carbons are also sp3. This is just additional information for you to know. The answers are this. Number 3, which is this right there, is an OH. It's very easy. This is an alcohol functional group. This carbon is sp3 hybridized carbon. The carbon is sp3. The functional group are carbon, meaning OH. Always if you see a carbon with OH like that, it is an alcohol. So that's an easy question to answer. So number 4 is an amine. An amine is in general, it's nitrogen containing. Remember, you have nitrogen, but here I have a different kind of amine. All of them are carbons. So you could have R3N, that means trialkylamine. You could have R2NH, dialkylamine, or you could have just RNH2 as an amine, or this is so this is a tertiary amine, this is secondary amine, it's a primary amine. So this is called tertiary amine because all of them are carbon. This is a secondary amine because it has 2 alkyl groups, meaning 2 carbons. Here a primary amine is just directly attached, a terminal amine. This is primary. So this is just a clarification for you to maybe when you are studying Org 2, it would be beneficial. So an amine group has a nitrogen. That is important to know. Number 5. Number 5 is this carbon-oxygen bond is double bond, which is sp2 hybridized carbon. So this is RCHO. So this is aldehyde. So this has RCOOH. This has RCOH. So this is an aldehyde group. This is a carboxylic acid group. So I can add more in this. In the future final exam, you might see groups like RCONH2. This is not amine, but amide. An amide group is a functional group as well. What else? So there are many other functional groups we would encounter, but for this test, these are the 5 functional groups shown in this compound. Okay? Now we'll proceed to the next question number. Okay, now question number 7 is a resonance question. It's asking you to draw a reasonable resonance structure for the following molecule. It's already shown as you see. This is a charged species, and you are asked to draw a major resonance and a minor resonance contributor. So you should be able to do by just moving this electron, pair of electrons from the oxygen to this bond, where you have this bond, and this has to move to this to satisfy that electron. So this resonance is, the result is this. So if you are also to draw another resonance from this to go to this one, you just move a pair of electrons out of this carbon-oxygen bond in this direction, you will end up getting this resonance structure. So if you just look at this structure and that structure, they have what is called charge separation. Charge separation. So structures that have charges rather than bonds are not major contributors. For example, this is not major, this is minor contributor as well. This is major because it doesn't have charge separation. A resonance structure that doesn't have that many charges on it, rather than charges, it has full bonds, like this pi bond, is a major contributor. That is the most stable contributor in the resonance. So this is minor. So minor because this is a plus and minus. So if you were to compare this minor and this minor, this is actually the least contributor. This is least. The reason is the two charges are very close, plus minus. This is plus in this carbon, and across all that, the minus is on this oxygen, the negative charge. So the charges are separated farther apart. So relatively, this is a minor, but least contributor would be this, where the charge separation is next to each other. On this carbon, you have a plus, on this oxygen. So this minus and plus are very close. That makes it very least contributor. So the major contributor in this resonance structure is this. I really encourage you to watch my video on the lecture on resonance, and you'll understand how to draw a reasonable resonance structure. For example, you don't if you have two structures that have negative charge on oxygen, for example, versus negative charge on nitrogen or negative charge on carbon, you can say this is a least contributor, this is the next one, this is better. So always negative charge should be on a more electronegative atom. There are some rules which are describing in that video, and I really encourage you to just go through those my video lecture on resonance. But for this question, this is a minor contributor, this is a major contributor, and also remember to learn to appropriately push the electrons. For example, here the electron is pushed that way, and this is pushed that way. And this, you are taking out electrons like that, and negative charge on oxygen, positive charge on carbon. Even then, whenever there is charge separation, the resonance structure would be a minor contributor, not major contributor. More bonds are better than charge separated species. Okay, we'll continue more now to the next. Okay, question number 8. It's showing this compound right here. This is a 1-ethyl 2-methyl cyclohexane compound. 1-ethyl 2-methyl cyclohexane compound. So how many distinct stereoisomers are possible for the following compound? Draw all of them clearly and assign the stereochemistry at each chiral center. Describe their stereoisomeric relationship, such as enantiomers, diastereomers, etc. So first, this cannot be a stereogenic center because it has 2 hydrogens on it. This cannot be, this cannot, this cannot. But here you have this carbon, carbon number 2, has 4 different atoms, or 4 different groups are attached to it. This is one group, this is the second group, this is the third, and hydrogen is obviously, there is 1 hydrogen there. So you have hydrogen also on this. So these are the 2 stereogenic center on carbon number 1 and carbon number 2. This is the stereogenic center. So if I have 2 stereogenic center and I have 2 to the power of 2, which is 4 possible stereoisomers, we have covered this in stereochemistry. So first of all, what are the 4 possible stereoisomers? 1R, if it is R position, and 2 position can have a 2R also. The mirror image of 1R, 2R is 1S, 2S, that are enantiomers pairs. And on the same 1R, I can have 2S, and the mirror image of that is 1S, 2R. Basically, I have outlined 4 stereoisomers, which are related as 2 enantiomers, and this pair is related to this pair. For example, 1R2R and 1R2S are diastereomers. 1S2S and 1R2S are not enantiomers but diastereomers. So I have 4 different stereoisomers. How to draw them? Here, if I put the ethyl group, for example, in a wedge coming to me on the plane of the board, and the methyl group going down, that would give you an R and an R configuration, 1R, 2R configuration. You could come up with how as assigned for R and R. So you should be able to tell that as well. Here, this is 1S, and here it is a 2S. You should be able to know also how to assign that. And this is 1R, and this is 2S. This is 1s and this is 2r. So basically these are the two enantiomers here I mentioned. These are enantiomers. Here are the other pair of mirror images, enantiomers. So as you know, enantiomers are mirror images. So for example, 1r, 2r is a mirror image is 1s, 2s. So these are enantiomers, mirror images, like these ones. And 1r, 2s, its mirror image is 1s, 2r. These are mirror images, mirror. This is the other mirror, is this mirror. So if two structures are mirror images, they are enantiomers. These are enantiomers. Okay? I think that would be enough discussion. So whenever you have two stereogenic center, to the power of 2 is 4. So the general formula is, if you have n number of stereogenic center, the number of stereoisomers is to the power of n. This is the general rule. Okay, now we'll proceed to the next question. Okay, now question number 9. Draw the equilibrium conformations of the compound shown, which is this compound right here. It is a trimethyl cyclohexane compound. So it has a 1, 3, 5 positions are the methyl groups at 1, 3, and 5. So, and give one of the more stable conformation and explain clearly why that would be the case. So if you remember, in cyclohexane conformation, there is a chair conformation, very important subject in organic chemistry, especially Chem 1. You should be able to draw a good cyclohexane chair conformation with a proper ring flipping, where all the axials, when you flip them, should go to equatorial. For example, if I do a ring flip for this is what I draw. So the proper ring flip, for example, if this is the case, this would be now axial, and this would be now equatorial. Right now, this is axial, this is equatorial. This is now equatorial, this is axial. So this is a proper, this is a ring flip, chair flip. We call it ring flip or chair flip. It always goes through the both conformation, a high energy equilibrium, but it goes from this to this conformer. Let me go to the question. Here I think I made a mistake labeling 1. This is 3. It should have been here, so that was a wrong structure. So just disregard the top one. So at one position I have one metal which is down because it is below the plane of this ring. So it is an equatorial down, so it's a relative thing. This is CH3 at carbon number 1. This is carbon number 2. At 3 position, I have another metal which is also down the plane of the board, inside the plane of the board. So this would be not axial, but should be equatorial. So this is CH3. This is carbon number 4, and this is carbon number 5. So at carbon number 5, it is on the top of the plane, because this wedge is coming towards me. So it will be axial because it's on top of the plane of the top. So the plane. So if you just consider this is the plane of where it is relative, so the CH3 is down, and this CH3 is down, this CH3 is up. So that's how you draw them, okay? Let me remove this. And now the ring flip would give me everything that was axial would go equatorial, everything that was equatorial would be axial. So this right here is carbon number 4. Here it is right there. This is 4. Okay? Just whatever was the leg of the chair now becomes the back support of the chair. So this is number 4. So this CH3 is now axial. Carbon number 3 now is, the metal is now axial. This number 5 is equatorial. This CH3 is now anaxial. Okay, now the answer to come up which equilibrium is more favored, obviously this left hand side equilibrium is favored. That's why I have the longest arrow towards this, but some amount to this. So this has one axial substituent, large group, one axial metal group, but here there are 2 axial metal groups. So that is unstable, not stable, less stable. I would rather say less stable, because there is a 1,3,1,3 diaxial interaction between this metal group, 1,3. There are 2 of them, 1 to this and 1 to that. So there are 2 1,3 diaxial metal-metal interactions, which makes it unstable. Here there is 1 axial, and this is hydrogen, 1,3, 1 and 2 at this position. This is 1,3 metal hydrogen interaction, not metal-metal. So here is, this is 1 position, or 1 position to 3 is metal-metal, 2 large groups interaction, which makes it less stable. So this is a 1,3 metal hydrogen, only 1. So this is more stable. So this is how you draw a more stable chair conformation for this compound. Okay? Okay, let's go to number 10. It asks us to draw clearly the S configuration of ketoprofen in the box. As you see here, ketoprofen, which is a painkiller, the biologically active compound has this stereogenic center. These are, for example, this is sp2, hybridized carbon. There is no stereogenic center, sp2. All of these are sp2, sp2. So there is no stereogenic center for sp2 hybridized carbon. All of them here. The only stereogenic center, which has 4 different substituents, are this carbon. This is the stereogenic center. So the biologically active ketoprofen is an S configuration. The R is not a painkiller. So it's asking us to fill this box with a structure where we are drawing an S configuration. Here is how I solved it, and this is S configuration. If you just look at here, the carboxyl group, the carboxylic acid, this is carboxylic acid functional group. This is carboxylic acid functional group, remember that, is priority number 1, for example. Priority number 2 would be this arm right here, because it's more substituted, heavy atoms. priority number 3 is this. Priority 4 is at the back, which is the way we want it. So if you just go from 1 to 2, that is counterclockwise. Counterclockwise is an S configuration. Okay, that's right. So the R configuration would be is just the mirror image of that. So if you were to draw the R configuration, you just draw something like this, where the COOH, the carboxyl group, goes back. CH3 is here, and the H group is facing towards us. So this is the R configuration. That's not what the biological active one. This is what you are asked to draw. So the difference between this stereogenic center and that is, this is an S, this is an R stereogenic center. Okay? With this, we'll continue to the next question number. So question number 11 is still in the area of stereochemistry, but it's a calculation of the optical rotation. The pure anti-malarial drug minus quinine, which has this stereogenic centers, 3R, 4S, 8S, 9R isomer, has an alpha value of, that's the degree of rotation, optical rotation, of minus 165. This is a reference one, a pure one. And the question is asking you, what is the percent EE, percent enantiomeric excess? This is EE is enantiomeric excess. If you are synthesizing a new anti-malarial quinine and you measured it to be minus 135, obviously it's not 165, but somehow you have most of it is as a pure quinine. You want to know the enantiomeric excess, meaning that how much excess is this over the other one, the other image. So percent EE, enantiomeric excess, is measured value of alpha value, measured alpha, measured over alpha, which is reference or known literature-wise. So if you just divide that and multiply it by 100, your enantiomeric excess, meaning that the quinine 3R, 4S, 8S, 9R is 81.8% is enantiomerically excess over the other one. The other one is the mirror image, for example, 3S, 4R, 8R, 9S. So this is not the desirable one. But when you synthesize, you only synthesized it to this excess of this one, which is your target. But on the way, you have also some impurity of the other enantiomer. So the enantiomeric excess you made is almost 81.8%. You have made a pure enantiomeric excess of the desired target. Okay, this is the desired quinine. You didn't make it 100%, but 81.8%. That is measured by optical rotation. So you measure optical rotation. And the device you use to measure is called polarimeter. In a lab, we use polarimeter to measure optical rotation of an enantiomeric excess can be calculated from that ratio. So this is EE percent. Okay? So we'll continue part B of the same question. This is part A. Next question is part B. Okay, part B of question number 11 is asking us, it's a continuation of the previous question, 11A. what are the percentage of the desired quinine and the other enantiomer, which is not the desirable one, the mirror image, which inadvertently synthesized while trying to make the pure one. So what are the total percentage? This is a percentage, how much they are. So first you have to know in the racemic mixture how much is in the racemic. Racemic means the minus quinine, which is this one, 3R, 4S, 8S, 9R, plus in equal amount is a racemic. So that is a mirror image, which you didn't think to synthesize, but obviously synthesized together, 8R, 9S. So this is in 50-50 is a racemic. So, but we already know the enantiomeric excess of this one, the excess enantiomeric of the desired one is 81.8%, right? So in the racemic, meaning that the both as a mixture, both of them exist, in 18.2% is racemic, meaning that they are both the desired and the undesired as a racemic. But enantiomerically pure one is synthesized 81.8. That means you just subtract 100 minus 81.8. The racemic is this too. But the racemic, you should remember, it is 50% of desired and 50% of undesired. So still the desired one has some mixed within the racemic. So the total percentage of the desired one in the racemic plus in the enantiomeric pure form is 81.8 pure enantiomer, right? But from the racemic also you have 18.82, since it's 50% divided by 2. So this is the racemic, which contains both ones, but divided by 2. This sum would give me the total amount of the desired, whether it's mixed or in a pure form, is the total percentage of the desired total. Total percentage is 90.9. So the undesired one would be, obviously, if this is 90.9, 100 minus 90.9 equals 9.1% is the other enantiomer in the total mixture. So this is how you answer. It's a little bit involving, but that's what you need to understand, what's the enantiomeric excess. So this is the major concept is EE, enantiomeric excess, racemic, are the two important concepts I want you to know in this question. Okay, we'll continue now to problem number 12, or exam number 12, question number 12. Rather. Okay, so the next question, 12a, it asks us to calculate the delta H, heat of enthalpy of the reaction given below. So if you remember in our discussion on the thermodynamics chapter, a bond that are broken are contributed as a positive, and minus the bond all made are to be subtracted. So the sum of all bond broken, the sum of all bond made, if you just subtract that, that is the delta H of a reaction. Because in this reaction with bromine, new bond, this carbon-hydrogen bond is broken. Carbon-hydrogen is broken. bromine bond is broken. These are broken ones. And in this compound, the one which are made are, I will just put them with the black one. So carbon Br bond is newly formed, this bond, and HBr bond is formed. So these are made, and if you just look at this, these are broken bonds. So basically, to make this tertiary butyl bromide, this bond, carbon-hydrogen, has to be homolytically dissociate. This bromine-bromine bond has to be broken, and this has to be made. So for this test, in this test, I have given the table. Here is the table, bond dissociation. This is the dissociation table. This is endothermic, meaning that you have to put energy in order to break, for example, a carbon-hydrogen bond, a bromine-bromine bond, a carbon-bromine bond, and HBr bond to be broken. So these are all bond dissociation. So you should be able to know the bond dissociation is positive. The top ones are negative, actually. So that's why we have this sign right here. So first, let's add bond broken. 403.8 is for carbon-hydrogen. 193 is for bromine-bromine, broken. That's endothermic, a plus. Minus bond made. Carbon-bromine bond is made, so that's 272. So that's minus 272. And 366 is HBr made, minus 366. So basically, in general equation, bond broken minus all of those bond made would give you the net delta H. So if you see here, you get minus 41.2 kilojoules per mole. So this reaction in the question, is the above reaction endothermic or exothermic? Obviously, it should be exothermic because delta H naught is less than 0. But if delta H is greater than 0, that would be endothermic. Delta H less than 0 is exothermic. Okay? So basically this question, usually you'd get a table of bond dissociation table. So in your book, in the final pages, you might find this useful table of values. So in the test or in the exam, I provide this, but the way you need to read it is important. For example, this carbon Br bond is made, so it should be in the negative side. So you should be able to identify what bond is broken and what bond is made. Other than that, it's just algebra. Plus, add all of the bond broken, add the bonds that are made, and subtract it. That would give you the net delta H value. So that's an easy question. So we proceed to the next one. Okay, now question number 13, and the question is, draw a qualitative general energy diagram for the reaction above in question 12 based on just only delta H values. You can calculate assuming the reaction has an intermediate. These are two important concepts here. The delta H value is exothermic from question number 11. And the reaction has an intermediate. So you should always remember transition state or activated complex, which is designated in this dagger symbol, and intermediate. So I start from labeling this. This is delta H, or energy. This is the progress of the reaction in that direction, or time of reaction. Now, since delta H value is exothermic, the energy of the starting materials right here, this butane and bromine, are at this point are higher than the energy of the products for exothermic reaction. So the products were, I believe this was bromine plus HBr was the products. So the energy of the products is less than the energy of the starting materials. That's why delta H is minus 41.2 by this amount. So the energy starts right here for the starting material. So you need to draw it very clearly. This is the amount of the difference between the starting material and the products. That's why it's endothermic. A reaction which has intermediate, which is this intermediate right here, this is what intermediate means. Not the one at the highest activation energy value. This is activation energy, EA. This is a transition state complex. These are where the transition complex is at highest energy. That is the amount of the activation energy you need to put in for the reaction to reach to this transition complex. But the reaction, since it has intermediate, is relatively stable intermediate. For example, in this case, it is a tertiary third butyl radical intermediate. So the intermediate is not this. And then that intermediate recombines with bromine radical, and from that transition state again would fall off to the product. So this is the energy diagram for with delta H value of exothermic, minus 41.2, and also which has an intermediate. But if you were to draw, for example, for an endothermic reaction which doesn't have intermediate, for example, for an endothermic one, you would have something like this. No intermediate, just transition state. For exothermic with no intermediate as well, you would have something like this. So this is the transition state. This is the transition state. So as you see, the shape is different. Here you have an intermediate, which is relatively stable. It goes through that. No intermediate for these two. No intermediate. Intermediate species. There are some reactions which doesn't have intermediates. This also is no intermediate. So remember the energy diagrams. To properly draw them, you should understand some of this concept. That's why I put them as a question in this test. Okay, we'll proceed now to question number 14. Okay, welcome back. Now let's proceed to question number 14. It's asking us to define what a Meso compound is. Explain with chemical structure or examples. So a Meso compound, as you know, it's a compound which has one or more stereogenic centers that are mirror images within the molecule. Because the molecule has internal mirror of symmetry, for example, in this case, the optical rotation, if you just totally measure the optical rotation of a Meso compound, totally it is zero optical, because rotation is 0, because it's basically a racemic mixture, but in a sense it is within the same molecule. So if we take this compound right here, if you have R and mirror image is S, and you have a mirror something like that, which is cutting equally half, this is reflected over this metal is reflected over that, this CH2 is reflected to this, everything is reflected to one another as a mirror. So a meso compound has a mirror within itself. That means there is internal mirror of symmetry. For example, in this case, if you just look at this as a mirror passing through this molecule, this stereochemistry, this are, for example, let me say, if this is S, if this is R, this would be now S, this would be R. That means this is mirror image to that, R, this is mirror image to that, OH is OH, this to OH are also this to OH. So if you pass a mirror, you are reflecting both the stereogenic centers as well as the groups or the atoms themselves, exactly the same. For example, this metal and this metal are mirror images, the same. This R is reflected over this would be S. So if you take a meso compound and someone asks you what is the alpha or the optical rotation for a meso compound, it is 0. Because this R would rotate the molecule, let's say left side, and this S right side in equal amount. Hence, the optical rotation should be 0 by definition. This is also another meso compound. Here you have this OH reflected to this OH. This OH is reflected to this OH. Say if this is S, and if this is R, then it is a meso compound. So you have to make sure that what the stereochemistry is right there and right there. I'm just giving you an example. But it's not only the stereogenic centers that should be mirror images, but the groups themselves also have to be identical. For example, if you have this group, CH2OH, and CHO, and if I have OH and OH, and let's say this is R, this is S, yes, the stereocenters are mirror images, RS, but the groups are not the same. Here you have CHO, aldehyde, here you have alcohol. So this is not a meso compound. So make sure that it's not only the stereogenic centers that are mirror images, but the groups themselves should be also mirror images to one. So OH is reflected right onto OH. This OH is reflected to this OH. And the mirror is passing through that. And if this is R, this is S. Let's say if this is S and it should be R, then this satisfies to be a meso compound. So let's recap again. A meso compound is a compound which contains 2 or more stereogenic centers, chiral centers, that are mirror images to one another because the molecule has an internal mirror of symmetry. Okay, that is a definition for meso compound. Okay, we'll continue now to question number 15. Okay, question number 5. Arrange the following compounds in order of decreasing acidity. So you have compound A, B, C, D, and this is an alkyne, pKa. This hydrogen right there, this hydrogen is what we are referring to. There is only one hydrogen on this acetylenic compound. By the way, this is sp hybridized and sp hybridized carbon. This hydrogen has a pKa value of 25, and this hydrogen has a pKa value. This is alcohol. Alcohols are in the range of 16 to 18 pKa value for that hydrogen in general. This is a carboxylic acid, obviously an acid, oxalic acid. This has a pKa value of 4.5. This is a sulfonic acid, pKa of minus 1.5 to minus 0.20. So based on our pKa knowledge, D is, so you are asked in decreasing acidity, so from the strongest to the weakest acid in this series. So D is the strongest acid, followed by C, followed by B, followed by A. So high pKa value, high pKa is less acidic. Low pKa value is more acidic. So that is how we order them. So this is a decreasing order. We are decreasing this direction from D, C, B, A. So this is acetylenic hydrogen, pKa 25. The acidity of this hydrogen comes because it's on sp hybridized carbon. Remember that in the future that would be helpful. This H is relatively acidic than this. This is on carbon. This is on oxygen. This has a carbon-oxygen double bond and OH functional group. So in the next question, it says explain the reasons for the difference in acidity between A and C. Both hydrogens are on oxygen, but it is asking you why they are that much different. So this is more acidic. So if you just do acid-base reaction, so if you just remove this hydrogen, you'll have this alkoxide. So if it was more acidic, the equilibrium is shifted mostly to this, but it doesn't like to give that H. But this one, this H, is easily donated and you can have this structure. So what is the difference? This alkoxide, negative charge, these electrons cannot be resonance stabilized. No resonance for this. But if you just take this after ionization, after it loses its proton as an acid, this is carboxylate anion. Carboxylate anion is resonance stabilized. Hence, this is more acidic. This is compound. This is between A and C. Oh, I'm sorry. So the difference is between A and C. But still, the difference between B and C is this. But if you were to compare between A and C, also, I can do that. So this is pKa 25, C is pKa 4.5. So obviously, the acidity is very large difference. The carbanion, for example, if you just take that compound, it's linear. if you dissociate that into its acid and base form, it doesn't really like to give that acid that easily. You have this one versus for C, you have this C is actually this OH. So when it gives off its proton, it's in equilibrium with O minus. So this is resonance stabilized. This carboxylate anion, as I said, is resonance stabilized. But this negative charge is not resonance stabilized, and the negative charge is on carbon. So this is less stable than this one. So this is resonance stabilized, but the anion that comes from acetylide, from acetylene carbon, is not resonance stabilized. This is not resonance stabilized, like exactly like I have the discussion here between B and C. Now I'm showing the difference between A and C. Not resonance stabilized. So both reasons are fine for A and C and B and C as well. So that's why the acidity differences are. But the general acidity is D is the strongest acid, and A is the least acidic compound. Okay, now we'll continue to the last the last question in this test would be the next. Okay, number 16 asks you which of the following compounds is more soluble in lipids. Lipids are hydrophobic compounds or hydrophobic substances, and which one is more soluble in lipids? As you know, this, if you just look at this is a highly hydroxylated compound. It is polar. It has capability of making hydrogen bonding. This can make hydrogen bonding. This can make hydrogen bonding. So these are more soluble in water-like compounds because they make hydrogen bonding. They are polar, and they are more soluble in water because they are also, these compounds are sugar compounds. This is sugar. But if you look at here, this is only this hydrogen, one group, an alcohol, but the rest of it is almost all of it is carbon-hydrogen bond. So that's aliphatic carbon-hydrogen bond. So they are hydrophobic. So these are only carbon-hydrogen bond. They are mainly hydrophobic. Since it's like dissolves like, they dissolve in lipids. So this compound is most likely to be solubilized in lipids. Lipids are fatty acids and so on. So the fat can dissolve hydrophobic substances, which are only carbon-hydrogen bonds. So this is the end of the test. I hope you found this answer key as helpful for future references, and I will be also putting the same for test 2 in few weeks, and I really encourage you to watch the videos associated with each one of these questions, as I have already discussed them with in detail. Okay, thank you so much.